So does it? Yes, it works. Fantastic. Yes. Very good. Thanks. Good. So thanks. Good morning, everybody. I hope you're not too hungry. Good. So thanks for being here. Thanks to the organizers, of course. That's really a pleasure. It's the first time for me in this beautiful place. And okay, so my task will be for these few lectures to tell you something about current research in acceleration, dark energy, and gravity. I'm Luca Mendola. I work at this nice place, University of Heidelberg. The weather is not as good as here, but we're also very far from any kind of sea or ocean, but still it's a very nice place. So I invite you to visit the place and my group. Good, so this is the outline of the 4 lectures. But actually there is a total continuity between all of them. So I will discuss some theory and some observation of dark energy. And dark energy is a very wide concept, essentially means all we don't know about the universe, so I cannot cover all that. Fortunately, several of the other speakers will cover many of these parts, so I will focus really on some theoretical aspects, but also observational ones, hopefully without too much overlap. I like to point out this text, you probably know, this beautiful work by Dodelson, and now the new edition with Fabian Schmidt, my own work on my own paper with Shinji Tsuchikawa about dark energy. And then there's a lot of interesting things on this Euclid theory review from the Euclid theory working group. Fundamental physics with the Euclid satellite is a title similar to some of the lectures we are listening to this week. All right, so, well, I'm surprised that I'm the first one to show this slide, actually, if I'm not wrong, because this is a mandatory slide, really by law, every cosmologist should show in the first 5 slides of your talk. You've probably seen this billion of times, so I'm just here to, give me the opportunity to say that mostly we will discuss something which is near here. This is the last epoch of the universe, of the evolution of the universe, and I want to discuss mostly things that happen here, which by no means means that dark energy is only important there. Dark energy is what we don't know about the evolution of the universe. So it can be that many effects of dark energy actually happens during the evolution at very high redshift, billion of years ago, and not just in the last few billion of years. Or if you prefer to think about redshift, unfortunately, these pictures are very nice, but they miss the most important quantity that we like in cosmology, which is redshift, typically. Don't know why. Redshift over the unit is here. Redshift over the hundreds is there. This is the 1000 that Fabio has been discussing this morning. So it's not obvious at all, and actually we mentioned cases in which actually, even Fabio mentioned already cases of early dark energy, which is important here. And you can have also, why not, effects. Actually, we study some effect of, possible effect of something that you can call dark energy, even before recombination. That's actually interesting that we can observe some phenomena in the recombination using the idea of dark energy, although a very non-trivial form of dark energy. All right, so, but for most of my talk, indeed, I will perhaps focus on relatively small redshifts. Now, this is a slide that had been, pieces of this have been shown already in the previous lectures, but just to be sure that we are on the same page, had to take some equation from standard cosmology. Of course, I cannot redo all of this, but as you have seen already in the previous talk, we define a Hubble function. This is the first Friedmann equation. The expansion velocity is proportional to how much density you have in the universe, except I'm simplifying already by assuming flat space. And for the first few, certainly for this lecture and part of the next one, I will totally assume the universe to be totally homogeneous. So we discuss perturbations only later on. So assuming that, we get Einstein's equation, we define density fractions, how much density there is in a particular component. So it will be an omega matter, and I like to possibly always write down 0 to say that we are talking about those parameters today, because in some equation you actually need omega matter or omega radiation, or omega lambda at every given time, but normally we think of them as the value today. And therefore, you can rewrite this equation in a more practical form in which you have observable things and parameters on this side, the expansion rate today, the fraction of matter, the fraction of radiation, the fraction of cosmological constant, and if you have other things to add, you simply add them, and each one of them already tell you how they dilute with the expansion, with the redshift. And the total, since there are density fractions, the total sum of those fractions must be 100%, so unity. So another way to rewrite this Friedmann equation is simply this: an overall factor and then parameters. How much density you have in a species I, and what is the equation of state, which is the relation between pressure and energy density. Now, this equation is very simple, but very, very useful, because it's very generic, very general. Not totally general, because this is actually supposed to be a constant here, so you can generalize even more. But it's nice because every time you think of a new component of the universe, you can simply add it there and just make a sum a bit bigger. And then you are automatically including in your calculations, in your code, in your analysis, new components with new parameters. So every time I say, and every time most people say, a cosmological model, we actually mean a particular choice of this omega I and a particular choice of this W. There's no limit to playing around with this. If you want to invent a model, you just write down a new omega, a new W, and force the total sum of the fractions, and then you see, go read the data and see whether you can make a discovery. Now, this is only possible because most of this is only possible because you have relations like this one. This is perhaps the most important one. There is another one similar for the angular diameter distance. I will focus on the luminosity distance today, and I'm sure you've seen this. Most of you that have been doing cosmology certainly have seen this, or just attended some basic course on cosmology. But again, just to be sure that I don't mention things that are completely new to you, I wrote down a few of the useful formula we're going to use. This is the very convenient relation, because this is the flux of a source, this is the luminosity, and this is essentially the distance you observe this. Now, flux is something you observe, is how much energy per second per square meters you observe in your telescope. So this F is always well known. This L is how much luminosity is emitted by the source, is energy per second. And of course, you need to assume something if you want to get some information on the distance. Or vice versa, if you measure the flux and you know the distance for some reason, then you can infer what is the luminosity of that source. Now, these two factors, 1 plus z squared, this is the distance that you get in cosmology, is the co-moving distance. And this factor 2, 1 plus z, is just due to the expansion of the universe. A source is moving away from you, so every photon that you receive decreases its energy because it's redshifted. And also how many photons you receive per interval of time also changes because the interval of time has a dilation effect because of special relativity. Although we reinterpret this in cosmology, the effect is essentially the same as you would have obtained when a source is moving away from you in special relativity. So these two factors simply tell you that the photons are a bit less energetic than emitted, and they come to a slower rate than with respect to the rate at which they have been emitted. So we define this luminosity distance, dl, and if you just take the equation for light ray, ds equals 0, I guess I didn't even write down the metric, sorry, but if you take the metric to be if you write down the Friedmann-Robertson-Walker metric and you try to figure out what is the evolution of a photon, you just have to put the null light equals 0, and then you get this relation between Fz and the various quantities, so which I rewrite simply directly already in terms of the luminosity distance. Now, this equation here, which is simply taking Friedmann-Robertson-Walker equation, putting ds equals 0 and writing down with other symbols. So it's the basic things you should find on page 3 of every book in cosmology. Tells you a very important thing, very important, that this distance is related to fundamental parameters of your evolution. This is actually written explicitly for, this is actually general, because when this is negative, there is an imaginary that converts a sign h into a sign. But whatever it is, the only important thing I want to mention is that this depends on your cosmological parameters. There is an overall factor, H0, which doesn't play a big role for what I need to say, mostly, at least today. But it depends on the curvature, and crucially, and more importantly, it depends on the entire expansion rate H of the universe, the one we just wrote down a moment ago. I just took a big square root to put this in evidence, this factor here, which you see, H divided H0 is exactly this. So all I'm telling you is that this quantity depends entirely on the expansion of the universe. Therefore, depends on your cosmological model. Every time you invent a new component, let's call it component X with equational state X, you put it there and you get a new dependence, a new form of the luminosity distance versus cosmology. And since this is unobservable, at least if you know something about the luminosity, so you can measure this, observing the flux, measuring the flux, and assuming something about the luminosity, then this is the most important relation that connects something that you can observe with theoretical parameters. Now, the crucial thing, well, let me tell you in a second. This is rewritten by astronomers in a slightly different way. They like to define an apparent magnitude and an absolute magnitude. So another identical way, another completely identical way, but with different assumptions, with different definitions, not assumptions, is that the apparent magnitude is related to the absolute magnitude by some numbers when you express this in megaparsec. This is only valid if you express this in megaparsec, otherwise there is a different numerical factor. All right, so this is essentially the same equation as before. The whole point is, again, that if you know the apparent magnitude, which is your flux, and you know something about the absolute magnitude, and that's where the difficult thing is, then you also know the distance, which means you can measure this distance, which means if your theory is good, it will fit the observed data. If your theory is not good, then you will not find the numbers, the values that are observed, as we will see in a moment. Now, this is also very important. Let's forget for a second about the curvature. We know the curvature is pretty small, so probably this doesn't play a big role. Actually, in the limit in which this goes to 0, this term and that term simplifies, so it is only a dependence over this. In fact, for flat space, I could have simplified everything by just deleting this, deleting that, and writing directly the integral without any function. So this integral, what I want to say, is the crucial part. So observations only give you this ratio, h over h0. Well, it gives you also h0, but they are different kind of observations. They are local observations, the local universe, the local expansion rate. But the past expansion rate, the one you really observe in the cosmological level using distance indicator, supernovae 1A, as we will see in a moment, only give you this ratio here. So observation gives this. All the rest means all the inference we obtain from this depend on the cosmological model. If your input is wrong, your output is wrong. If you put a constant W, you get a result from data analysis, but if W is not constant, you will not see it, and you just get a biased result, biased by your assumption. This is a recurrent theme in my lectures. I'll try to point out how many times we make assumptions in cosmology. And since cosmology is full of assumptions, because unfortunately we cannot make many experiments running new universes except in our computers, then we have to make lots of assumptions. That's the nice and the nice part, and the interesting part, the exciting part, but also the weak point of cosmology is that we have to make many assumptions, and we have to remember once in a while to just check them before proceeding onwards. Good. So I can start again with another. I'm really surprised. I'm the first one to show this cake here, right? Is that true? Or did Fabio show it? Wow. So I'm the first one to show this one, which again you have seen more than 1 billion times before. But it helps me to make a first inventory or executive summary of all of cosmology, since I will use later on at some point these numbers, maybe to make a calculation, to show a plot. Of course, we should have a look at what they mean. So at the moment, it seems that most of the observations can be fit, and I've discussed some of this, by an amount of matter which is roughly 30%, but we need to distinguish between baryons, 5%, and the rest dark matter, and we need to do so because, as you will see, or I don't know if I mentioned it, but certainly from CMB and from Big Bang nucleosynthesis, we know the baryons, that means essentially protons, constitute only a few percent of the entire cosmic recipe. So we know this by some almost direct information from nucleosynthesis and CMB as well. Fortunately, they agree. And from other observations, the one I will discuss, we know that the total sum will be roughly 30%, but this part is only a small percentage. So we have matter composed by two things. And the thing that make them in cosmology, in many calculations put them together, is that they obey they have the same equation of state. They are both pressureless components or no relativistic components. Then we know that massive neutrino probably constitute just certainly less than 1% of the total universe. And we know that by various indications. I think we have seen also this in Fabio's lecture. The amount of there was a moment in which you mentioned the temperature of neutrinos. And since you know the temperature, you know the distribution, you also know the energy density and the number density of everything. And if they have a little mass, as we know today they have, they cannot go beyond 1% or so of the entire universe. Then there is also a little bit of fraction of photons. There are also some people called humans that pretend to know anything about all this. And the space curvature apparently is very close. So this is what we know from various indications, many of them from CMB. And of course, the big question is, what is the rest? What is the 70%? Remember, if you convert all this into omegas, density fraction, the total omegas must be unity, 100%, and you see there is a 70% missing from these numbers there. So the content of my lectures will be trying to think about this 70%. What could that be, and what could teach us if we use this opportunity to go beyond what could be the simplest possibilities and to see whether we can learn something more about the 70% and along the way also about physics beyond the standard model. Now I mentioned several times the word the question of state. I didn't define it explicitly, but it's just the ratio between pressure and temperature. I'm sure you know, but let me write down so in case I can refer to this question once in a while. This should be a parameter, but everybody likes to call it an equation. So, although the question, you cannot read, I guess. The question is this, we call the equation the W itself. Can you read? It's very, yeah, what? Yeah, it should be black one. Not really make big. Okay. And we call this equation of state. Good. So, well, then we can make a cosmic inventory of this. Baryons and cold dark matter are supposed to be pressureless, so equation of state roughly 0. And the reason is that obviously if you're talking about non-relativistic matter, the density is proportional to c squared, the most important formula in physics, as we saw this morning. So this is proportional to c squared, but the pressure is proportional to v squared, velocity squared for non-relativistic particles. So this is totally negligible, which means W is essentially 0. For radiation, the opposite is true. They're the same order of magnitude, as we know from statistical physics, black body distribution. Planck law is 1/3. For massive neutrinos, it's changing in time because they're massive and the distribution depends on the evolution of the universe. And because they were in equilibrium at the early universe, so there was relativistic earlier, not relativistic today, but they play very little role. Now there is something that I will discuss, of course, but I anticipate the cosmological constant. And the cosmological constant, at least at face value, or in other words, if you really just take the cosmological constant, don't generalize it to dark energy, as an equation of state of -1. And if you want to consider curvature as well, you can say that curvature is a sort of fluid, although it's not a fluid, it's a geometrical effect, which has an effective equation of state of -1/3. Now, I'll just make this list as to say that we can really complete the cosmic inventory the executive summary or whatever you call it, by a list of the entire cosmological model. So if you are able to fill this table to be sure that every number we put here is really correct, then essentially we have found the goal of, we have fulfilled the goal of cosmology, which is to fix the cosmological model. So a cosmological model is essentially a list of these things there, unless there is something more, of course, that we might consider later on. So that was the introduction to the introductory lecture, a compressed version of what we know and some hints of where I want to go and discuss later on. Well, the main question we want to now discuss in the next few slides is something about this cosmological constant. Even before I introduce it from the observational point of view, the famous discovery of acceleration, I would like to discuss the idea of a cosmological constant in general. And for this, we go back to the classics. And the story starts many, many years ago, 350 BCE. Unfortunately, there were no Nobel Prize at that time, so Aristotle didn't get one, but I should have deserved a dozen or so, because it was wrong in everything he said, practically, concerning physics. But all what he said is still interesting today. Even if it was wrong, that's really the sign for me of a great scientist. You can be wrong, but still say interesting things. Okay, well, he had a problem. He noticed, maybe it was the first, to notice that there's something always attractive that we call gravity, which was even called gravity at the time. And if it is attractive and there is nothing to resist, how we can avoid that the sky falls on our head? And really, Aristotle wrote down exactly those words, more or less. And if you read the initial, sorry, I like this because I like history in general. That's my passion beside cosmology, so I always like to take the opportunity that you cannot protest too much to tell you something that goes in my mind, and I normally don't have many opportunities to teach this. And anyway, so the point is that if you read the few lines at the initial of the famous work by Aristotle on the sky, the cello, you read, why the universe is not expanding. You read those words. He asked himself, well, he didn't say universe, he said why stars is not flowing away from me or going down to the earth. He posed himself this question, what we would say today, why the universe is not expanding. Of course, it is expanding, that was wrong, but it's amazing that he thought, he posed the right question, why the universe is not evolving in front of our eyes, why we don't see stars flowing away or going back. Well, flowing away, that was interesting because Aristotle, again, being wrong, it was right. He thought, there are also things that go up, not just go down, like smoke goes up. So he thought of something that goes up and something goes down, but he thought, why stars don't go up or go down? Why we see the same constellations are the ancient Babylonians, which were ancient also at Einstein and also at Aristotle's time. So he had this knowledge from the ancient Babylonians, constellations are always the same, so the universe is static. And another thing, it's not only static, but what do stars do on the sky? They don't go away, they don't come down, but they rotate. Is there any other thing on Earth that rotates without an engine, without a motor, without a horse, without you walking? No. So he realized that stars have something really weird. Don't go away, don't fall, and rotate around us. What was the conclusion? There must be some new material around, something which is nothing that we see on Earth, but that should be called quintessence. He was totally wrong in all he said, but he got the right direction, that there's something that we have to understand better about the universe around us, because it doesn't behave the way we would have expected based on local laboratories, on local experiments. Second story is Newton. 2,000 years after, he had exactly the same problem. Gravity is always attractive. How to avoid that the stars fall on our head? He was very precise now. He really mentioned stars, why they don't fall on each other or go back or go towards the Earth or whatever. And the answer was a bit somehow less insightful than Aristotle's answer, because his answer was initial conditions. Maybe stars don't move around because they've been set precisely by some intelligence in such a way that they just stay more or less there, don't move much. And then the story more or less ends for this part, for what I want to say, with Einstein, well, only a century ago, amazingly. And he had exactly the same problem. Gravity is always attractive. How to avoid the universe fall on our head. And if you read Einstein before the discovery of the expansion, he had exactly the same problem Aristotle. I'm sure he read Aristotle because he says at the beginning of some, I remember if it was a letter or an article, he says, well, the ancient Babylonians told us the constellations that we see today are exactly the same 4,000 years ago. They describe the Ursa Major, and the Orion, and they describe it more or less in the same way that we see them today. So how comes the universe didn't change? The universe must be static. So Einstein thought how to make the universe static. And his answer was that you had to modify GR equation introducing a form of repulsive gravity, because gravity is attractive. If that's the only force, it's hard to make things static. If there's only one force and the force has only one sign. So you have to modify his equations. Essentially went back to Aristotle and said there must be something new that is giving a shape to the universe and which is not in our, was not seen before. And now, this is the famous Einstein equation with the famous cosmological constant, which is just for no observational reason, can be introduced. Einstein introduced it for a wrong observational reason. He thought the universe was static, and that's the only reason why was that they didn't know about the expansion of the recession velocity of galaxies, only knew about stars, they didn't know about the existence of a galaxy, So, so that was an observational reason, but it was a wrong observational reason. But still, he actually realized that you could add this just by mathematics. You write down an equation, you discover there is another term which has all the nice properties. It's covariantly conserved, is covariant in the sense as the right number of indexes, so transforms in the correct way, is covariantly conserved, and doesn't disturb too much what we know. That means Poisson equation, Newton's gravity, doesn't disturb too much if this lambda is sufficiently small. You want to recover Poisson equation from relativity, of course, and you can do so if this lambda, this extraneous term, is simply small enough not to disturb Newton's gravity. Now, he wrote down this paper in 1917. He says somewhere here in German that he had a crazy idea, fantastische Auffassung, means a crazy idea. He wrote to the sitter, and he wrote down this crazy idea in the sense of this term. You know the famous joke about Einstein's biggest blunder when he introduced the cosmological constant because of the expansion? And I understand it. His biggest blunder was this. He wrote a lowercase, but we know that it's capital case. That was the blunder, because it was absolutely correct. You can't do that on the equations. You can't do that. You could have done this before, and forced by no argument except mathematics. You could have done, therefore you should do it, in the sense that, well, if there's a possibility that mathematics allows you, then you should use it and see whether the data constrain it or not. Now, this cosmological constant is still with us today, as you will see, essentially explains many things. But really from the start, I like to point out that we know still so little about the universe, although we think we know, because you see tables with parameters and measurements so precise, 1% and so on. Yes, but all this, it's also could be misleading, not necessarily. This could be, because what we know from the universe comes from essentially from only three epochs, from Big Bang nucleosynthesis, very early in time, so this is omega radiation, so the universe was dominated by radiation essentially disappeared. Matter, which is dominated universe for a matter-dominated epoch, and today is going down because dark energy is taking the lead. And the sum of these three curves is always unity, because I'm forgetting about curvature. So when the dark energy takes the lead today, this is today, and dark matter should decrease. This is the density fraction. So don't confuse yourself. Dark energy, if it is a cosmological constant, is constant. But what is constant is rho. And this omega is rho divided rho critical, so it doesn't have to be constant, it's not. All right, so we know things in a detailed way only at the epoch of Big Bang nucleosynthesis, because we can observe the relic abundance of light nuclei. At the CMB epoch, the one that Fabio is telling us, around 1,000. And recently, by looking at large-scale structure, evolution of the fluctuations, in redshift of order unity, so in this very recent epoch. All the rest, we have some indirect information. For instance, CMB, we know that it contains information on the line of sight, so it's mixed in, but it's a line of sight information, so it's integrated out to the CMB. So what I really mean to say is that most of the information in cosmology comes from these three epochs, and there is still lots of uncharted territory between them. So that's where I think is interesting to look for new adventures, new discovery, new things. So the first reason for me to go beyond the simple cosmological constant is indeed just because there's still lots of things we don't know. And we don't know whether here something happening crazy, some matter goes down, or some dark energy, early dark energy, for instance, as we mentioned already, be non-negligible in the early universe or even before. So there are many things that we would like to be sure that we know, and the space of discovery is still very large, I would say. That's the first reason. Another one that I like to mention is very controversial, that's why I like to mention it, is the coincidence problem. If you write down the change of omega lambda as a function of time, this time is a special time, it's the logarithm of A, you call it e-folding, but think of it as time essentially, is a time adapted to cosmology. Then if you write down this derivative there, you discover that dark energy has been, this derivative has been 0 for all the past universe, will be 0 for all the future universe, as not 0 only essentially today. And you can see this from the previous slide. All I mean is that if I continue this will reach unity, and then we stay constant, this will go 0, and they stay there. So the only moment in which this is changing is essentially only today. Today is this line, and we are close to today. This is redshift 0.5 or so. So this is this strange coincidence that the dark energy seems to be active, let's say, only today. Of course, it will be also in the future, but the fact that it's having an evolution, a dynamics compared to the other components, only essentially today or recently. Now, this is controversial because you can rewrite this plot because it's a graphical thing. So if you can rewrite this plot in many ways and you don't know how to estimate whether it's likely or unlikely, and whether this is the correct time, and whether you can make statistics out of this, or how coincidence, how uncertain, how unlikely this coincidence is. Is it really a coincidence or not? So there's plenty of interesting philosophical debate about this, but somehow for me is an indication that maybe there is something we don't understand. Maybe dark energy is having a big impact today and not earlier or later because there is some reason. Maybe there is an interaction of this extra component. So it's a good indication that there might be something that we need to understand better. So this, of course, also the other fundamental argument that people often point out in this context, which is the famous fine-tuning things. And the reason is that if you evaluate the amount of dark energy or this cosmological constant or whatever that is, today we discover that this rho times lambda is very much smaller than than rho in Planck units. Now, why should this a problem? Well, because if we imagine that there is an energy lambda, which is essentially, if you can see from this equation, lambda can be defined as what happens. Imagine you move this on the right-hand side, and then you say, let's take a universe which is completely empty, so put this to 0. Then this is a new source. So you can think of this as a source field that is left when there's no matter around. That's why it's called also vacuum energy and can receive an interpretation in quantum field theory. But since we don't know really how to deal with this, we imagine that if there is a process that creates in the universe some vacuum energy, this process should be related to the famous Planck units, because that's where we imagine that quantum gravity, quantum field theory, and generativity should meet. So if there is a fundamental process that creates a vacuum energy, we expect this to give rise to a vacuum energy of order 1 in Planck units. But instead, observationally, we find that this 100 minus 10 to minus 120, this quantity here. So from a purely very qualitative point of view, it's hard to interpret this as something fundamental because it's so far away from the only fundamental units we have around in nature. So either there's something we don't understand on this side, the theory is completely wrong, or there's something we don't understand on this side, maybe what we measure is not what we think it is. So there are various reasons why this cosmological constant is a very interesting thing, a very interesting concept, of course, but maybe we should be open to other possibilities. Right, so the next thing, of course, is to play with this. We are still on very general level. I still haven't discussed really observation very much. The next thing will be, of course, to play with this. One say, well, okay, now this W is -1 for a cosmological constant. let's imagine now play with a different W, but still I want to have that this maybe can even be changing, but still I want to have a so-called barotropic equation of state. The pressure depends only on rho. And so I can play with that, of course, it's very nice and funny. For instance, you can take a behavior of this kind, which I even has a name, Chapligin gas, but for now I just want to take it as an example. And therefore in this plot P versus rho, you can draw a line like this and can continue and go on this way. And this is the cosmological constant line, P equal to minus rho, right? W equal to minus 1. So this is the one we started with, the cosmological constant. Now we invented a model which is totally different, of which P versus rho is related by this. But now what happens? This curvature here should be curved in this way because you want a positive sound speed, and the sound speed is the P over the rho. So you want to have this kind of curvature. But if you put this kind of curvature in the conservation equation, the same that we've seen in the previous lectures, then you discover that if you start on this side, you will end up here. And if you start on this side, you will end up there. And you cannot cross, because trying to cross means that when you reach this point, this goes to 0, so rho dot stops. So any universe with this particular equation of state will become a cosmological constant universe. And every universe with this equation of state that starts on the other side will also become a cosmological constant. So the cosmological constant is actually a kind of attractor in this space of parameters. So it's not so easy to invent something which doesn't go down to cosmological constant. And if you think in terms of potential for a scalar field, that is similar to say that if you have a potential, the one we've seen in the first lecture, for instance, if you have a potential and think of this as a potential for some field, V as a function of phi, then every time you reach a minimum, then this is a cosmological constant because V will be equal to constant. And this will be exactly the role of a vacuum energy. It's the energy that is left when the minimum reaches its ground state. So every time you draw a potential blindly like this, you will put a minimum somewhere almost by default, and default when the universe evolves, it will roll down and will stop there. Will oscillate a bit, it stops there. So essentially, that's another way to say that the cosmological constant is practically an attractor for most cosmological model, for not just cosmological model, for even drawing potentials like this or inventing an equation of state. So you have to do something more than that. You have to perhaps introduce a potential which has no minima, very weird, or an equation of state which cannot be written in terms of P versus rho, or something else. And we will see some of these ideas later on. So as you see, already from the start, even without doing much connection to observation, we see how many possibilities, interesting possibilities are there around, how many assumptions we're often playing with, and it's important to have a look at them critically. Now comes two warnings, also related to this idea that we should keep our eyes open. And the first warning is that one has to be careful with what you write down in the questions, because not everything you put in an equation is necessarily observable. Consider the simplest possible universe. Pressureless matter, uncoupled means no interaction with matter, and something else. Then the equation of state of this something else, if you don't know anything about it, just want to figure it out what it is, can be written in terms of this famous ratio that I mentioned before, essentially Hubble, dimensionless Hubble constant, in this way. So indeed, this is the observable. If you know this and this and you know this, then you can measure that, but you notice that there is still a parameter left there, omega matter. So even a perfect knowledge of the expansion rate is not sufficient to obtain W. One needs also omega matter. But all you get from this distance is E, not omega matter. Therefore, you have to choose. Either you know omega matter somehow, and you obtain W, or you know W and obtain omega matter. You cannot have both. Why it seems, reading most papers in cosmology, that you can get both? Because you are assuming many things. You assume, for instance, that W is a constant. Or you might say, well, there's plenty of papers that tell you that W is not a constant, as one of these simple expansion in evolutionary law, like the Chevalier-Linde-Polanski. such that W changes with redshift. Yes, but that also is a very narrow parameterization with 1, 2, 3, 4 parameters. So if you have 1, 2, 3, 4 parameters, but you can obtain observations at 10 values of Z, then of course you can measure exactly those 5 or 10 parameters. But my point is slightly different. What if you have no idea what W is and you don't want to parameterize in a specific way, because every parameterization simplifies things. We need to do parameterization at some point, but every time we do a parameterization, we should be aware that we are killing a large fraction of possibilities just because we make a parameterization out of many possible ones. So if you now just don't make any parameterization, try to figure out what is W without knowing omega, then you discover strange things like this. If omega matter is so this is a lambda CDM with omega matter 0.3, so lambda CDM means that W, which I don't know why it's called omega here, but it's a W. It's -1, and omega matter is 0.3, and that's what the real cosmological model is. But if you don't know that omega matter is 0.3 and you say the omega matter is 0.3 plus 0.1 or 0.03 or minus 0.1 or 0.03, and you try to obtain your W from observation, you will not get -1, because -1 is only obtained in this particular, when you know this. You get one of these strange behavior, including a singularity. So totally wrong. So that's because I'm not trying to make any parameterization. I really try to ask myself, what is the information I get from observation if I only have an expansion rate, and the rest just comes from theory, and I imagine at this moment I don't have a theory for W, and in fact we don't. So that was warning number 1. Be careful about what the are assumptions and how many things we take for granted, but they are not. Of course, maybe they're right, maybe W is constant, therefore we should just simplify our life, but I would like to be sure about that. Second warning is this. This is a strange plot in which I put size and mass of structures. For instance, humans are there. I hope it's correct. I took it from this work. Earth, sun is somewhere here, galaxy, quasars, atom, virus, light. Light is actually on this line. Is logarithm of size and logarithm of mass. Size means wavelength of light, of course. All right, so, and what is the region of this plot that we can really experiment with, that we really observe directly? Gravity in particular, sorry, I'm focusing on gravity. Where can we make experiments involving gravity? Well, essentially from the solar system down to particles, but it's very difficult to do experiments, gravitational experiment with particles, so sort of at the level of molecules, atoms we can do, but not much below. So let's say this is the region we can explore. We are exploring directly with gravity. You see how much is left out. This region is left out because if you try to squeeze this mass below this distance, you end up in a black hole, and the black hole only gives you 3 numbers. It forgets about all the rest, and all black holes essentially look the same except for the mass. So you cannot really play with structures in this region. You can also play with structure in this region because if you take a box of this size, and you try to put a light particle with a mass below this value here, you discover that you cannot, because the mass of the particle will have a Compton wavelength which is larger than the box. So you cannot simply keep a particle there. So you cannot make experiments there anywhere, with any tool. So we are only forced to experiment in this triangle, and in this triangle, only this region has been actually considered so far. So it's clear that only just referring to gravity, and all I'm talking, yes, thanks, and all I'm talking for this lecture is essentially gravity. Then, of course, there's plenty of space, plenty of things to still consider. And to be slightly more specific, and because it will be useful later on, let's imagine the simplest possible modification of Newtonian potential. Instead of 1 over r plus a correction, which is called Yukawa potential. And this is characterized very conveniently by a strength beta and a range lambda. So it's very easy to visualize. It's a force, a new force, which has a new strength in addition to gravity beta, and has a wavelength, a range of the order of lambda. If there is the size at which you're making experiments is much larger than lambda, this becomes a very small number, and you don't see this. If the strength is very small, also you don't see this. So it's clear that there are regions of beta and lambda which are satisfy experiments, and region of beta and lambda that don't. And they come from laboratories, collects years and years of very ingenious experiments, typically done with a Cavendish torsion balance, or modern version of it. And as you can expect, there are regions of high beta, which are for every lambda, some region of high beta is excluded, because if it is too strong, then you will see it in these gravitational experiments. So just by writing down this, you can expect there should be region of this form which are excluded, and region on the other side which are still allowed. If beta is too small or lambda is too small, then you cannot see the effect in your laboratory, so you still cannot constrain it. Now, these experiments now, including solar system tests and things, go from micrometers to parsec, essentially, including really everything, all the possible. So this is a kind of big plot which goes like this, trying to join together two different plots, microphysics and larger scale physics. And but still, you see, there's plenty of region to play about, in particular on very large scales, which are cannot be observed by this kind of experiments. So this thing, which will happen to have a physical interpretation later on by next lecture, is an example of how much we can still experiment with gravity. But there's much more, still a couple of minutes, or there's much more than that. Because think again about this form, and now I rewrite it. Instead of a range, I put a mass, because you can in fact make a theory of a scalar field, and you end up with the mass of the scalar field being there, which is the inverse of the range of this extra force. And if that's what you have, then this beta and this m, which are typically assumed to be constant by experimenters, don't have to be constant at all. They could depend on time, could be large in the past and small today, so you don't see it in laboratory. They could depend on space, so you might not see them on Earth, but see them elsewhere. They can depend on local density. They can even depend on species. It can be that experimenters are making observation with atoms, and actually it happens that maybe atoms or baryons don't feel this extra force, but dark matter does. So there could be many ways so that even if you have a strong correction, modification of gravity, you can term, it might even be that you cannot observe on local experiments. And maybe it's better to stop here. This will take me 2 minutes. It's better to stop here, because next one will take a few minutes. I don't want to rush. So, okay, so thanks. That's it for the first lecture. Thanks a lot.
Hello.
Yes.
Here in this Yukawa modification,
Yes.
you're mentioning dependencies on the potential dependencies on the local density. How about non-local dependencies? Would they be excluded, or?
Non-local. Yeah, that would be a possibility, but that would be much more. So you want to have a similar form from a non-local gravity, from non-local effects, non-local Lagrangian? That's what you're asking? Yeah, you can do. All the model I know actually can be reduced still to this, because many of these so-called non-local actually can be written in a localized form. But people also insist that there are really non-local field theories, and I don't know whether you can put in that form. But this is just one example. It's one possible modification of gravity, the simplest one. So your question is a complicated one. You can have modification different from this in general, and you can have some of these modifications arising from non-local theory. Yes, so the answer is yes, you certainly have.
Thank you. And I have a second question. Yes. You were mentioning this fine-tuning
yes.
problem, and there is this work by, excuse me, this constant expansion of the history model, this CT.
CT model, yes.
This CT model. Yeah, well, and what would you say about this?
I think they're not consistent with observations, although there are different claims, I know about that. But every time I look in detail these kind of theories, I think that's not sufficiently grounded on observations.
Yes,
That's what I might say,
it
yes.
seems that from CMB you would expect there's indeed a shift in the moment that happens. It's a little bit...
But even
maybe.
supernovae, I think, are not consistent with the RT cosmology, although...
But from a theoretical point of view...
there are also theoretical problems, but that's... sorry. Yeah? There are also theoretical problems, the fact that the metric with an RT looks a lot like Milne's model, and yeah, I know. But my answer would be, it seems at the moment is not consistent with all observations. Sure.
Hi, thank you. How would you relate this modified gravity in the form of Yukawa potential to dark energy? Like, well, how this specific type of interaction can mimic?
You want to do all the next 3 lectures?
Okay.
That's essentially what I discuss.
Okay, then the other question was, you said that we are only sensitive to the ratio of Hubble parameter to Hubble parameter today, this E. But on the other hand, we know what Hubble parameter is today, so we somehow measure it. Can you?
You mean H naught?
Yes. Can you please explain me briefly what the qualitative difference?
Yeah, but E is exactly what H naught is not. So E is exactly H divided H naught. So you see, I'm factoring out what we know because it's not so important for what I need to say.
Yeah, I see that in all your slides, only this ratio is relevant.
Exactly.
But in this case, in our universe, we could say that H0 is 1, but we know that it's something in meters over.
It's an overall fact. It's an overall quantity. It doesn't really...
Yes, but how why are we sensitive to this?
To H naught?
Yes.
Okay, different observation. Well, then you have to really know this is the Hubble law, the expansion rate in the local universe. So it's the limit. Well, there is H naught. Let me go back. There is H naught here, but it's only important in every equation. There is H naught, but it's only important it's a quantity that only gives you the overall scale, and you can measure it either because you know the overall expansion or simply because you measure the derivative at the present time. And you make so with Hubble law, measure velocity of galaxies and distance. The problem, of course, is that to be at very small scales, but very small scales are also the inhomogeneous ones. So the very complicated, and the reason why there is so much discussion about the value of H naught is that it's not obvious that we have been able to subtract the inhomogeneities from the estimation of H naught. So local observation are certainly sensitive of H naught, and consider that this is a job done, since we have very high precision measurement of that, beside the controversy, and now focus on the rest. Why? Because the rest is what contains the parameters, the cosmology of parameters. So I don't know if that answers. Thanks.
Okay, I wonder what happened if the gravity is not only attracted, but also it, as Newton say, it depends of the initial condition. And this is one question. And another question is, as you mentioned, essentially just that one supernova are model independent, the rest as model dependent. And so all this dark energy comes from that observations. But if there is a systematic or an evolution of the that 1A supernova, what happened with the dark energy?
Yeah. So the first question, I'm not sure I understand that. You mean?
Me neither.
That should be the right answer for almost all questions. I don't know. So I really don't understand. We mean initial conditions and repulsive gravity are two different things. Initial conditions is what we have to insert in every question. So what has no relation with what gravity is doing afterwards. So initial condition is up to, let's say, us or something to set up, and then we have to evolve. If we evolve with attractive gravity, then then it's difficult to explain acceleration. If you put a repulsive gravity like cosmological constant, it's not really a repulsive gravity, it's only a background level you can interpret as a repulsive gravity, but you cannot make a planet out of cosmological constant. Otherwise, to be much more complicated. If you play with scalar field, with strange coupling, then you can indeed invert the sign of that beta, have a negative beta, then that would be an effective repulsive gravity. You can do so, but it's very problematic. For instance, if you want to do so with a scalar field without interaction, then you have to introduce a phantom scalar field with a negative kinetic energy, which opens up an entire class of other problems. So it's very difficult to insert by hands a really repulsive gravity that really works in the sense that you make an object and this repels test particles. You can do so, but then you end up in many other problems. And your second question was about, I forgot. Supernovae, that would be also part of my lecture, but of course, if supernovae, well, we assume they don't change much because the spectra remains more or less the same. So it's difficult to figure out why supernovae are changing dramatically, and they give more or less the same, they belong to the same class of spectra, so it's difficult to imagine something like that. So you can test many things, as you probably know, as we know. You can test whether the spectrum depends on whether the dust makes the spectra depends on distance. You can measure this and constrain it. Apparently is not sufficient, any of this, to make a systematic effect. Other systematic effect, like lensing, which goes indeed with the distance, actually mostly works the other way around. It makes them brighter rather than dimmer. We want to make them dimmer to avoid the cosmological constant. Systematic effects in our theories is plenty. For instance, if there are big voids, you can change all of this because this is homogeneous universe. If there's a big void, you cannot apply. So there are many ways out. Yes, we all assume the supernovae 1A are good, either a good distance indicator or we can test how much not good they are. And we assume they're really good. So far, we don't have any evidence to the contrary. On top of that, there are indication from other experiments, CMB and things, and they all converge, as we will see soon.
Excuse me, just one quick comment, because there was this question regarding the universe and Newton's perspective. He also argued that the universe had to be infinite, so that there was no center of gravity where to collapse to.
Okay, but the reason why there's no collapse anywhere is because the initial conditions were set up in such a way that there's no place to collapse. But it's true, they also thought, well, since it's infinite, there will be an infinite, well, he says, since an infinite, it will be an infinite attraction from both sides, therefore they stay there. But in order to have an infinite attraction, you have to argue also that the initial conditions were special. So it's a complicated story. Thanks for the comment.
It was a very nice discussion and question. With two very interesting lectures. So please, let's thank Luca and Fabio again for the demonstration. And now we are all heading for lunch. So please follow the leader. And yeah, I will catch up. I will close the door. If you want to keep your things here, I think it's safe. Well, for sure it's safe, so don't worry. Unless you want to carry your bags, we're going to close the door. So lock the door. So.